In this video, we're going to introduce an iterative method to solve the Helmholtz equation, the so-called Jacobi method. It's not a very good method, but it serves as a nice illustration about what exactly an iterative method is and how it works. So to make our life a lot easier, we're going to focus on the 1D situation, the 1D Helmholtz equation. And I'm also going to introduce a shorthand notation. So say our grid has the following form. The grid starts at the first grid point x0, and then the grid size is delta x. So the field at the ith grid point like this, I'm going to introduce a shortcut f sub I here. That will make our life a bit easier. And then we know that we can write down the discretized version of the 1D Helmholtz equation. See previous video as follows. Fi plus 1 minus 2 Fi plus Fi minus 1. So that's a discretized version of the Laplacian. And then we have delta x squared k squared Fi, and this thing is equal to 0. So how are we going to try and solve this equation in an iterative fashion? So the first thing we need is some sort of initial guess, and I'm going to indicate that by the fields at all positions I at iteration 0. So this thing here on top is the iteration number. How do we construct an initial guess? Well, many possibilities. Either you can give that field just a random distribution or put it to 0 everywhere, or base yourself on some solution of a slightly similar problem that you know. Many possibilities, doesn't really matter. The important thing is that we have some initial field distribution as an initial guess. And then the whole method basically boils down to starting from a certain iteration n. How do we go to the next iteration? So how do we go from iteration n to iteration n plus 1? And that's the whole magic of the Jacobi method. So what does Jacobi proposes us? Well, he proposes us to look first at this thing on the left-hand side of this equation here and evaluate that for your current iteration. So we start off with iteration 0, but in general, let's look at iteration n. So if we evaluate that equation for a general iteration n, we have the following: minus 2 Fin plus Fin minus 1 n plus delta x squared k squared Fin. Now this left-hand side of that equation basically tells you how far away we are from the true solution, because we want this thing to be 0. So this can be thought of as some sort of an error term telling us how far away are we from the correct solution. How do we go from the current iteration Fn to the next iteration Fn plus 1? Well, Jacobi tells us that we take a look at this error, and based on the size of this error, we make an adjustment. So the adjustment is given by the following. So it's the difference between the new fields Fin plus 1 and Fin and the previous field. So this difference is proportional to the error we make with some sort of proportionality constant alpha, which is called the relaxation parameter, and which by convention is a positive number here. So this is the recipe that Jacobi proposes us. The question is, does it make sense? If this thing actually converges, will that guarantee that we have a solution? So pause the video and think about this for a while. More specifically, think about what happens if after a number of iterations you converge, and therefore the difference between the next iteration and the previous iteration becomes small. Can you then indeed find it plausible that you have a solution to the differential equation? It's pretty obvious if you have convergence. So if this thing doesn't really change after you do the iteration, then the difference between these two things becomes very small, and in the limits becomes 0. And if this right-hand side is 0, that also means that the left-hand side is 0. And that means that the distribution that you found and that no longer changes is actually something that satisfies the 1D Helmholtz equation. So you can conclude that if you find a solution, if the thing converges, if nothing changes anymore, then there's a pretty good chance that you find a good solution to the Helmholtz equation, which you can then verify. Let's now turn our attention to this relaxation parameter alpha. Pause the video and think about the influence of this parameter. What happens, for example, if you make it very small, very big? What are some advantages, some disadvantages? So think about that. So let's have a look at what happens if we, for example, take alpha to be a small number, if we decrease the value of alpha. Now, from that equation here, we can see that the difference between the old fields and the new fields is basically proportional to the error divided by alpha. So this is going to be 1 over alpha times a number. So you see that the smaller you make alpha, the bigger you make these steps delta f. Now, what does that mean? That means that, yeah, you take bigger strides through your solution space. So there's a chance to end up quicker at a solution simply because you don't take baby steps. So that's a positive point. But a negative point there, a risk, is it could be that your steps are so big that you jump, for example, over the optimum. So if you consider this to be like an optimization problem where you're looking for a minimum of a function, if your step is too big, you can jump from this point to that point and then basically just miss the optimal solution. So there's a careful trade-off here between large values in alpha and small values of alpha, computational speed versus chance of missing the optimal solution. Okay, in the next video, we're going to look at the stability of this thing here, because obviously what you want is that if we start from a finite initial guess, that after a number of iterations, then you still get something which is finite, because that's obviously a prerequisite for having convergence of this method. But that's for the next video.